This is the final part of Lesson 27 in heat transfer. In the final part of Lesson 27, we will look at Example Problem 1234 in your textbook. This problem can be found in the end of chapter problems in Chapter 12. We will put our knowledge of the spectral and total hemispherical emissivity of real surfaces to the test by thinking through and working this problem. On with the lesson.
This is actually a problem in the end of chapter 12 in your textbook. So I thought that we just talk about it together. So I'm going to give you 3 minutes to think about this. And then I'll let you talk about it with a neighbor and we'll talk this one through. All right, so see if you can think it through the next 3 minutes. Anybody have any thoughts that they want to share on how they're approaching this? Chase?
I thought they would both go up. Because what if the UC product goes in, the F would go up, that would mean like the total emissivity would go up.
So you're thinking that the F, the fractional black body emissive power function, F in some wavelength band, that thing. So this is a number always between 0 and 1. So does that change it? Like there's a limit on how much it can go up, and you have to pick a band in which it would go up. Does that make sense? So it is possible that this number would go up if the temperature, does that make sense? But this is a number between 0 is less than this number is less than 1. But it does have kind of something to do with this, right? How this function changes. It's fractional emissive power function. Other thoughts on, yeah, Daniel?
I think so. Almost one day, like you set that one with the A and B like above the other one, and like at some point it'll highest emission will be under B and so it's going to be under A.
Yeah, so Daniel was talking about kind of layering on top of the spectral emissivity on top of the spectral black body emissive power function, and then looking to see how they compare. I think that's a pretty good idea. So we can, I'm going to tackle this 2 ways. I'm going to tackle it Daniel's way. The other way I'd say is, we're not given any numbers for the wavelength, but we could just pick one for the purposes of thinking it through, right? And then we could apply our band approximation idea and just kind of see what happens if we kind of almost get quantitative with it. So I don't know, if I just picked, let's just say 2 micrometers, right, as kind of the crossover point here. And then we could approximate this as, well, the spectral emissivity is high, right, in that wavelength band, and it gets lower in that wavelength band. And I kind of pick a number that represents somewhat of an average. B is the opposite of that, right? It's just a flip of that. So we could go in and see kind of what happens for that particular case. So if I had to draw B, maybe I would draw B as this. I cut it like that, right? So that's the B, and this is A, and it's a band approximation of the actual curved data. Which is how we get quantitative. Okay. So let's go in and do both of these and see if hopefully we should get the same answer. So what Daniel was suggesting was drawing a graph with 2 axes, right? Wavelength on both axes. And on the top, kind of drawing in epsilon sub lambda and let's just do material A. Okay, so that looked like this. And now we have to think about different spectral emissive power functions, and we have to pick 2 temperatures because we're trying to say something about what happens when temperature changes. So why don't we just pick a big temperature? This is 3000 Kelvin, right? See, it's got a peak that's shifted to the left. So maybe at 3000 Kelvin, it looks like this. Right, this is EB lambda, the spectral black body emissive power. And then at a lower temperature, say 300, right, there's a huge shift in the peak power because this is a logarithmic scale. So here we were peaking around 0.8 micrometers. Here we're peaking around 9 or 10 micrometers. So if I had to draw the 300K, it would get shifted way over here, and it's a lot smaller as well. So this is like the 300K. And let me draw this a little bit more dramatically. So it's like, okay. So the idea behind this calculation for the total emissive power, it's this, I was talking with Garrett, I'm saying you can some ways I think of it like a weighted average because it is a weighted average. We're basically weighting the spectral emissive power function by the spectral emissivity. So this is how we calculate the total emissive power function from the spectral one. And so we're taking the epsilon lambda and we're multiplying by whatever the corresponding value of the spectral emissive power is at that particular wavelength. Right, so it's like I take whatever the value is here and I look down, right, and I multiply by that number. So if these are both big, then the numerator is big. If either one of these, if either the epsilon sub lambda or the EB lambda is small, then the numerator is small, and it's going to make a smaller epsilon, right? Because the base of this is just fixed by right. It's just a normalization function. So what I see here, when I look at this, the spectral emissivity is a larger number, right? When the spectral emissive power function is large at high temperatures. But over here, when the temperature is only 300 Kelvin, the spectral emissive power is a lot smaller. Yeah, so at 300 Kelvin, the total emissive power is going to be much closer to the value of where the purple dots line up, because that's where the thing is non-zero. And at the higher temperature, the total emissive power is going to be closer to the value of the spectral emissive power when it's larger over here, because that's where they line up together, right? So it's like, this is kind of telling you what the values of the emissivity are going to be. And when you weight this, you're going to end up with a higher number, right, for a higher temperature than at the lower temperature. So by that argument, we could just say this has got to go up, right, as temperature goes up. Like the total emissive power is going to go up as the temperature goes up. And because that was material A, I think, right? Because material B was just the inverse of that, it's got to flip. So for material B, the spectral emissivity was actually larger, right, at the wavelengths where power is coming out at lower temperatures. And so you're going to end up with a higher total emissive power when the surface has a lower temperature, and a lower total hemispherical emissivity when the surface has a higher temperature. Okay, so that's one way to think about this. I think that's a really good approach. I like that approach a lot. But the other approach is to try to get more quantitative and just think in terms of our weighting function, right? And we said in a band approximation, you could take this and say, we could break this up into, right, whatever the spectral emissivity is for the first band times the fractional emissive power for the first band, plus whatever the spectral emissive power is for the second band times whatever the fractional emissive power is, right, for the second band, right? If you look at your handout from last time, that's exactly that's the equation for calculating the total emissive power. Okay. So if we just say that lambda is equal to 2 micrometers, right? Then again, we can pick kind of two temperatures and see what happens. So if lambda is equal to 2 micrometers and T is equal to 300 Kelvin, okay, let's go in and see what the values of these fractional emissive power functions are. So lambda T is equal to 600 micrometer Kelvin, and I need to get the book up. Okay, so at 600 micrometer Kelvin, F from 0 to lambda is basically 0, right? It's 0 to 1, 2, 3, 4, 5, 6 digits. So if I go back to my work, right, what this tells me, we're going to do work for T equal 300 K right here, right? So F 0 to 2 micrometers, in this case, is 0. If that's 0, what's the fractional emissive power from 2 micrometers to all the other wavelengths? Alex?
1.
It's got to be 1, right? Because if there's no energy in this band, the energy's got to be in everywhere else, right? So you can always do, whenever you have a lambda 1 to infinity, f lambda to infinity is always equal to 1 minus f 0 to lambda, right? If we have 2 bands, whatever isn't in this band has to be in the other band. So that tells me that f lambda to infinity is equal to 1, because this one was 0. So if I go and look at my equation for calculating the total emissive power, right? Because this value is 0, it's like we have 0 plus whatever the value we say is for the other band times 1. So the total emissive power is going to take on, right, the value of the spectral emissive power in the band at the higher wavelengths. So that's this band, right? So for material A, it's a lower value than material B. Yeah? So if we kept going with that, if we wanted to say, look at 3000 Kelvin, right? We have to go do the same calculation. So now we're going to say T is equal to 3000 Kelvin, which means lambda T has got to be 10 times bigger. So now it's 6000 micrometer Kelvin. And if we go look at the table, got to go find 6000. Here it is. Right now, the first band fractional emissive power in the first band is like 0.74. So F0 to lambda was 0.74, which means F from lambda to infinity has got to be 1 minus that, right? So that would be 0.26. So now we would calculate the total emissive power as 0.74 times whatever the value is in the first band plus 0.26 times whatever the value is in the second band. So you see, it's going to be much closer to the value in the first band because that's a bigger number, 0.74 than 0.26. So the total emissive power is going to be closer to whatever the value is in the first band. So now it flips because now A is bigger and B is lower. So we conclude the same thing, right? The trend of the spectral of the total hemispherical emissivity, if we had to make a little plot now, of epsilon, no sub lambda as a function of T, right? As the temperature goes up, this should go up for material A, but it should go down for material B. Yeah, makes sense. Do you see how that happens? So this kind of highlights why I say I think about this as a weighted average. Yeah, see, it's like a weighted average on whatever the values of the spectral emissivity are, and we're weighting it based off of where is most of the energy contained, right, in the spectral emissive power function. Is the energy contained at low wavelengths or at high wavelengths? Questions on that little review? You can. This is really fundamental, I guess, and it'll definitely help you for. Perhaps would have helped you for the assignment due yesterday, but certainly for the assignment due Friday as well. Yeah, Chase.
Wait, so the spectral emissive power is the regular EY or B1?
Sorry, did I say I meant spectral black body emissive power?
Okay.
Yeah, you're right. The spectral emissive power has no sub B. That would be the real emissive power. So we weight it on the spectral black body emissive power.